Hi, it's review time. We're going to take a look at an active FET probe today. It was sent into the mailbag, but I thought I'd do a separate video. Thank you very much, Euler Precision. They're a Swiss company. No, it's not Euler Precision. It's Euler, as in Leonard Euler, like the famous Swiss mathematician, physicist, whatever. Yeah, very famous name. So it's pronounced Euler. Euler Precision, they've got this new eSAP-30 active FET probe. This is an engineering sample here, not for sale yet, but I'll link in their crowd supply campaign. You can sign up for it and get it when it's released or whatever. So thank you very much. Let's take a look at this. Now, I've done videos on active probes before, so I'll link those in if you haven't seen them. There's various measurements and things like that, but oh, look at this. Isn't that a thing of beauty? A joy forever. Look at that. So we've got it made in Switzerland. Made in Switzerland. Oh, hi to all my Swiss viewers. So an active FET probe, of course, very useful if you're doing anything over maybe, let's say, 500 megahertz. That's where your regular times 10 passive probes seem to stop. Yes, you can get passive probes that go to 700 or even 1 gig, but you're really after an active FET probe because they've got much lower input capacitance, and it's all about the input capacitance. Let's go to DaveCat. And I've done videos on passive probes as well and how they're constructed and all the rest of it. But basically, when you're measuring stuff with whatever probe it is, when you're measuring high frequency, the capacitance, the input capacitance of your probe matters. And these active FET probes, they're quite low. Look at this, at like it's 1 megohm input impedance, but it's less than 3 puff or 3 picofarads there. So very nice, not as low as like some of the other like really expensive commercial probes out there, but still it's going to be better than your typical passive probe. Now, of course, when you've got input capacitance, when you're talking about AC at frequency, you're talking about capacitive reactance, or what's known as AC resistance. You can think of it that way. So a capacitor has resistance at frequency. So in the capacitive reactance formula, classic one, you should know it, 1 over 2 times pi times the frequency you're talking about times the capacitance. The frequency is in hertz, capacitance is in farad. So let's just take an example of 1 gigahertz signal here and a 1 puff or 1 picofarad. It's called puff in the industry if you didn't know. If you want to sound smart in the industry, yeah, it's a couple of puff, you know, not a couple of picofarads, couple of puff. 1 picofarad input capacitance, even though this is 3, but we'll just round it to 1 picofarad, then you whack that in, it's 159 ohms. So your 1 megohm input impedance of your probe is suddenly gone to 159 ohms. You could come a gutser, that could really load down your circuit. So the lower input capacitance, the better. And active FET probes, instead of just having a coaxial cable, they will have a little FET amplifier in the front end here, hence active FET probe. So it's an active circuitry and a very short input cable, so you minimize your input cable capacitance. So it just allows you to have, even though 159 ohms is still low, it's still way better than a coax cable. So what do we get in the box here? We get the active FET probe made in Switzerland. Look at that. I like how the cable doesn't come out the end. That's interesting. It comes out the side like this with this MMCX connector here and MMCX connector on the input, so you can hook up various probes, which we get here. But there you go. The good thing about this is that this can plug into any standard oscilloscope, 50 ohm input oscilloscope. If your oscilloscope doesn't have 50 ohms, well, it should if it's a 1 gigahertz, you know, in gigahertz bandwidth probe, or you can use just an inline 50 ohm terminator. Because the problem with most active FET probes on the market, this is an old school Keysight / Agilent one, is that they will use the custom interface. So they actually draw power from the custom interface. This is the Keysight / Agilent interface here, and this is an active FET probe, very good. This one here is only a 2 gig bandwidth. The new Euler Precision one is 3 gig bandwidth, but you can see the input capacitance is 1 picofarad there. So it's, you know, it is lower, but you pay a lot more for this active probe. If you have to ask the price of this, it's many thousands of dollars. You probably can't afford it. And they all look and feel kind of different. This one has the active FET amplifier right up in here, of course. It's got some little, looks like a little, like a shrimp or something, you know. It's got like little LEDs to light up when you're probing these things. But generally, you're not sort of like, usually with these probes, you're not just like probing around your circuit, just willy-nilly kind of thing. You're sort of like setting up to do proper measurements. And that's why it comes with a little tripod-y thing. How does that work? There we go. Does that snaps in up? No, that snaps in there like that. There you go. And then you've got slots in the side here, and that either goes like that, or you can tilt it down like that. It's a bit how you're doing. I would have preferred to see a standard 1/4-inch thread tripod mount there, so you can, you know, use other solutions to do that. That would have been nice if they had the 1/4-inch insert in there. Anyway, we do have a note. I'm Enrique Corpa from Euler Precision. Follow your channel since 2012. Thank you very much. He was starting out. We're a small team of electronics engineers creating high-quality test instruments focused on functionality, compact design, right to repair, and open source software. Awesome. So this probe will actually be open source, but not at the outset. It's only when it's like made obsolete by a subsequent model, then they'll release it for like long-term right to repair kind of thing, which is still pretty good. So we've got the prototype. This is battery power, by the way. So yeah, you don't need an external USB cable to power it. And there's a crowd supply link. I'll link that in for those playing along at home. I assume that you can sign up and just get announced when they've actually released this thing. I'm not sure the actual price. It's probably under like 1,000-ish or something like that. Whereas in your big end active probes, they're like many thousands of dollars. So yeah, I'm sure you're going to save a bit with this. You can update the firmware in it, apparently. I'm not sure why you'd need to, really, because it's just like an amplifier in there, and Bob's your uncle, pretty much, and how to charge the thing. So with active FET probes, it's all about the accessories you get with them, how you actually probe it. Usually, if you know you're going to probe your high frequency circuits with an active probe, you will typically actually design in test points, test connectors directly onto your PCB. But if you don't, then you can use like little pins and flat flex cables and other things. Anyway, we've got an MMCX to MMCX connector here, MMCX to UFL connector here. So, a UFL might be a typical one you might put on your board or something like that. So you can just, plug in your test point straight on your board. And we've got some little flat flex jobbies like this, so you could solder those directly onto test pads on your board, or you could, if you're getting desperate, you'll like scrape off some of the solder mask on there or directly on the pins of a chip or whatever. So you can solder those directly on, so that goes to the MMCX. And they've got like a little adapter board here, so you can just put some like hard pins on there and just probe like that. Typically you might do it yourself probe, you get a paper clip and you bend it, cut it to size, and bodge it on to your circuit. So active FET probes come with little accessories like this, but often it's a do it yourself job depending on your particular requirements on your board you're probing. And there's quite a few like do it yourself active FET probe designs out there and stuff like that, but one of the things about buying like an off the shelf thing, it's more polished and it's designed and measured. So we've got like a measurement report here. For this particular serial number one, I assume each one would come individually serial number tested like that. If that's, that's really cool to keep management happy, let me tell you. Anyway, we've got our gain measurement here, and you can see, there's not much variation over the frequency range. This is 1 gig here. So, it starts to drop off as it approaches 1 gig, as you'd expect. And once you get up to 3 gig, there is a little kink in the response there after 2 gigs. So if you're after extreme precision at 3 gigahertz, this may be not the best tool in the shed, but anyway, it's decently flat, and they've got the actual magnitude figures here. Yes, this is a 10-to-1 probe. And the input impedance measurement, we've got our return loss, so we're just an S parameter measurement here. Got our little Smithy chart, and the green is the response there. And it was absolutely perfect, 50 ohms across all frequencies. You'd expect a perfect circle here. It's on the bottom side of the Smith chart because it's capacitive, not inductive, which would be on the positive chart. And you can see That's a pretty decent response there. These are at the different test frequencies there. And you can see it sort of curl up at the bottom there. That would be an artifact of that steppy response there between 2 gig and 3 gig there. But you can see the claimed input capacitance is well under the 3 picofarads that they claim. So not too shabby. And they actually give you an input impedance plot as well. Nice. So you can see, like at that 1 gigahertz we're talking about, 159 ohms for 1 picofarad, because it's a bit higher than 1 picofarad. You know, it's still quite low-ish, but not as bad as a passive probe, let me tell you. Okay, let's measure a real-world signal using the Keysight HD304 MSO. This is a 1 gig bandwidth scope, 14 bits, beautiful jobby. Of course, we've got the Agilent N2796A probe on here, so I'll use that first. I've got the little low inductive tip like this, and this one has the probe built in, and we'll just probe the clock on this Altera Cyclone 2 here. It's this little crystal oscillator jobby here. It's only in quote marks, only 50 megahertz, but because it's a square wave, it has frequency components going into the gigahertz range. So it's all about the wave shape we're looking at. So I'm going to probe the output here. There's a tiny little via right down in there, if you can see it. I'm going to probe that sucker, and the ground on top of the case, I've actually checked, it's actually connected through to the ground there. So we can probe that easy peasy. Okay, we're at 5 nanoseconds per division here. This is with the Agilent Keysight probe. Let's probe that. Haven't put the ground on yet. I'll put the ground on. There we go. Beautiful. Look at that. So we can capture that and we can compare it, but you can see not a perfect wave, is it? There's lots of look in the middle there. That could ruin your days. We're of course not going to fuss over the implications of this particular signal, but it works, but it's got those high frequency components in there on the edges. Look at that. That could be a PCB layout thing. That's likely a PCB layout mismatch issue. So I'll capture that and we'll probe it with the Euler Precision. And yes, of course, we are limited by the 1 gig bandwidth of this scope here. We're not actually limited by the probe, but if we get a same result, but what we're looking for is a same result that matches the much more expensive Keysight probe. And herein comes your problem with the supplied probes. There's no real way to get, well, not with the supplied accessories, like to get a really direct tip connection like I could get with this Keysight probe. Like, you know, here it is, right? The FET input amp is just here, right? So there's hardly any inductance happening in that. But I've had to use this flat flex adapter, which is fine, but you know, you're going to add like inductance in here. So we expect to see not the same signal fidelity we're going to get. If we were able to, like if they supplied a board that just had like a couple of little pin connections on here, I could have then just probed it with my tongue at the right angle and using a very short path. But anyway, let me show you what I've got. And you can see that we are seeing these high frequency components here, right? But we've got this extra ringing. If I actually disconnect that, this is actually a real-time signal. You can see that, you know, we're getting some ringing up there, but it is very small compared to what we're getting here. And this is not the actual design of the probe itself. This is the probing. And therein lies the rub with high-frequency probing and active probes. It's all about the probing. I'm sure the frequency response of the amplifier that they're using in there is as advertised and schmick, and it's, you know, flat as a tack and everything else, but that probing, just, you know, that additional probing there is causing that. So it's not the probe, it's Dave's dodgy probing. But you can see that we are getting the high frequency content in there. So that's pretty groovy. So I could get a better result than that, but I don't think I can do that with the supplied accessories. They just, you know, maybe I could take this board here, because this actually, I do like the design of how this actually, you know, just plugs directly in there like that. But what I'd have to do here is actually bodge one of these, like actually cut off the flat flex and then just have like a pin extending out there. I can actually try that, and I can show you that by just fiddling with the probe here. I can just put my fingers on there. Look at that. Because we're doing basically some compensation there on that probe and we're changing its characteristic response. It's all about the probing. Right, I just cut off that, added a little pin there, so we're not too shabby, and this is not as long as it looks. I'll actually touch the top of the crystal, which is grounded onto here, so I should be able to probe that. So, tongue at the right angle, let's go. All right, let's probe this thing. Let's see if we can get this. It's live. There's our signal, and if I can get the ground on there, there you go. Ah, it's looking schmick. Let me capture that. Winner, winner, chicken dinner. Now, the blue waveform is the one that we had before. There you go, with that big flat flex thing on the end of it. So, and we've still got the orange one on there. And look, the green one is the new one. You can see it's almost matching perfectly. I can zoom in on that perfectly. The orange Keysight reference in there. Look at that. That is beautiful. And these impedance mismatch artifacts down in there, that's near perfect. Look at that. Wow. So, there you go. It's just as good as the more expensive Keysight oscilloscope, but it's all about how you probe it. And to get that, I had to do a direct probe like that. And if I turn off the dodgy probing we saw before, you can see it here. And just comparing the noise floors here, let's short out the yellow on top is the Keysight. The bottom is the Euler. They're both 20 millivolts per division. So Euler's definitely lower noise floor. So let's take this bad boy apart. It's got a nice green LED here, which I assume turns red if you've got low battery. Haven't even charged the thing. Of course, we've got USB-C on the end for the 18650 inside here. Oh, we've got screws. And there it is. Now, they did mention in an email that this is injection molded by the looks of it, but they mentioned that they might do, I think it is, or maybe it's professionally 3D printed. Anyway, the case for the first like 100 units or something might be 3D printed or something perhaps, and they might be nickel screened as well. They might shield the case because they had a report of some excess noise or something, which I'm not seeing, so I'm not sure what the deal is. Anyway, standard 18650, you can replace that yourself. Nice. So let's get the rest out. And this is interesting. That is conformal, whoop, out of focus a bit. That is conformal coating. You might be able to see, yeah, the gloss there. That, why they've conformally coated that, I'm not sure. Not for moisture ingress, because that is not the amplifier, but they have actually gunked all of that. Looks like we have our switching converter under there, but what we really care about is that's where it all happens. That is our front end amplifier there. Looks like we've just got the one chippy there. We'll have a closer look in a minute, and that's our output there. So we've removed the solder mask around there. We've got our controlled impedance tracers, and I'll take a closer look of what that jobby is there. But that's essentially, that's all you need. Really, the rest of it, it's not like this has like an adjustable DC offset or anything like that. Nothing fancy-pantsy like that. It's just a high-speed amp, and that's it. Yeah, and the rest of it's basically just power, really. And there it is, and that, tilted at the right angle, that is a Buff 802. It's upside down, so all the electrons are going to fall out. Nothing fancy-pantsy here at all. I do like how they've used the wide capacitors there. Why do they use those? Lower inductance. We have ourselves a little trimmer there, a little Burns jobby. Nice. But that is basically the entire front end there, and it goes out here, and the rest of it is just meh. There's a couple of bodge wires on there, but this is a sample, like a pre-sample prototype, so yeah, you expect that. But the rest of it we don't care about because it's not part of the signal chain, so really, meh. And of course, this thing is not isolated in any way. It's not like a proper, it's not a high voltage probe, because the problem with active FETs probes is this one's plus minus 25 volts input, which is pretty good, I think. But if you go over that, you're going to blow the arse end out of it. So yes, that is not isolated to the USB, and it's not isolated to the output either. You wouldn't expect it to. That's not its job. So, as usual, I've done a video on this, and that's how not to blow up your oscilloscope and how not to blow up your active FET probe either. And if you want to see what one of the best passive probes is like, this is the Roden Schwartz Jobby 700 megahertz analog bandwidth. Doesn't get much better than that. I think Tech make one that is 1 gig, and I've probably got one here somewhere, but I'm not going to get it out. But anyway, 700 megahertz bandwidth. So let's probe and see what we get. You won't get nearly the fidelity of the 1 gig active probe, let me tell you. Got our Keysight reference waveform there, which is identical to the Euler probe, and there's signal incoming. There we go. There's the 700 megahertz passive probe. You can see the amplitude is down drastically because this thing is loading it down. It's got too much capacitance on there. You can see that you don't get any of the high frequency content in here, and that amplitude is completely gone ski. So yeah, it's like, what is the input capacitance on this? Yeah, 9.5 puff, 9.5 picofarads. So yeah, you can see the difference between an active probe there and a passive probe. You're just not going to see it. This is one of the best, most expensive passive probes on the market. As a rule of thumb, over 500 megahertz, but even less than that, then active probe is definitely the way to go. So there you have it. That's the Euler Precision made in Switzerland 3 gig single-ended active probe, and it's not a bad bit of kit at all. I really like it, so thank you very much for sending that in. I'll link it in down below. Seems to perform very well, just as well, if not better, than like my Keysight reference one here, which is many times the price of this one. It's the eSAP-30. As I said, probably the only thing missing is like a better selection of like direct like contact probes and ground solutions and things like that. And I would have liked to have seen like maybe a 1/4 inch thread mount integral in there. That would have been nice. But apart from that, that's a winner chicken dinner. I give that a thumbs up. So if you like that video, give this video a thumbs up and discuss down below and over on the EEVblog forum, and check out eevblog.store for my merch. Catch you next time.